Hello, Math Studies students, and welcome to your online lesson. Today we'll be talking about relations and functions. Specifically, we'll be identifying functions and using functions to find unknown values. We'll start off by talking about what a relation is. So a relation is a set of points that contains two variables. So a way that we could list a set of points, there's a number of ways to do it. One is to actually make a list where I use something called a brace. It's got that little squiggly or like gull wing sort of shape, but it's called a brace, or multiple ones we call braces. And I could just write ordered pairs. So I could have an ordered pair of like 1, 1, where I have two variables, like an x and a y, just like when we, list ordered pairs in a geometry class or in an algebra class. And then I could have another set of ordered pairs, like 2, 3, another one, 3, 5, so on and so forth. And that right there is a relation, because I'm relating an x and a y and saying that the 1 goes with the output of 1, the x of 2 goes with the y of 3, the x of 3 goes with the y of 4, so on and so forth. Some sort of relationship. I could also write these as like a t-table, where I have x's and y's. And so I could have like 1, 1, 2, 3, 3, 5, 4, 7, so on and so forth, where again, I'm relating two variables, an x and a y. And lastly, I could also make this into like a little graph here, where I could just plot these points. So I go over 1 and up 1, put a point there, over 2 and up 3, put a point there, over 3 and up 5, put a point there, over 4, up 7, and then I could essentially connect those, and now I've got a graph of this relation. And then my second bullet point here says the relation is often expressed as an equation with two variables. So I could do that as well. I could write an equation for this. In this particular equation, for every x value, what I'm doing to it is I'm doubling it and then subtracting 1, in order to get my y value. So that would be another way to express this relation here. And you can check that. So let's take a random one like my 3, 5. If I plugged in a 3 for x, I would have 2 times 3, which is 6, but I'd get minus 1, which would leave me my y of 5. So again, 2 times 3 minus 1 is going to get me a y of 5. So this was my input, and that was my out. All right, a relation must have an input, often x, and an output, often y or f of x, and we'll talk a little bit more about that later in this slideshow. And this essentially makes a relationship or a relation a number changing machine. And you saw me do that a moment ago. I plug in a 3, I get out a 5. I plug in a 4 over here, and I get out a 7. So it takes an input and does something to it to make it into an output. Again, as we saw before, the x and y values from a relation create ordered pairs, which are coordinates of a point. And again, we can put those on a graph, or we can just make a list of those, or any of those sorts of things. All right, so let's look at now what a function is. So what is a function? Well, the function has all of the properties of a relation as shown on the previous slide. However, a function must have exactly one output for every input. Exactly one output for every input. And so most things that we look at in a math class are functions, but not every one of them. And it must, again, have one output for every input, and we'll look at some examples of that coming up. A function is sometimes referred to as a mapping, since every input can be mapped or paired with exactly one output. So how do we know if something is actually a function? Well, if we have a graph, it's really easy using something known as the vertical line test. And the vertical line test states that a vertical line can intersect the graph of a function at no more than 1 point. Right? A vertical line can intersect, and intersect means cross, the graph of a function at no more than 1 point. So let's take a look at what this looks like in our first example. So are these functions? Well, the first graph that we have is sort of this curve that is, extending up as we go through here from left to right. And the question is it a function? Well, I don't need to know too much about this. It's most likely an exponential type of graph, but The important thing is that I pass the vertical line test to know if it's a function. So I'm going to draw a vertical line. A vertical line is one that goes up and down. Okay, and you can see that I intersected the graph at exactly 1 point. All right, well, I'm going to draw another one. Well, again, I'm only intersecting at 1 point. Let's move to a different area. 1 point, 1 point, 1 point. Is there any spot on here where I can draw a vertical line where I will intersect the graph at more than exactly 1 point? And no. So is the first one a function? Yes. This is a function. All right, moving on to our next example. This one looks a little bit more interesting. It's got some curves. It goes up for a while as we move from left to right, and then it has a maximum, comes back down, has a minimum, and then it goes back up. But the question is, despite all of its weirdness, is it a function? So I test the vertical line test again. So I'm coming down here, and I intersect roughly there. Now I intersect here. The maximum intersecting at 1 point, 1 point, 1 point. Right at the minimum, I'm intersecting at 1 point, 1 point. So I can draw a vertical line anywhere here, and am I ever intersecting at more than 1 point? No. So again, this is definitely a function. It passes the vertical line test. All right, now we have our last one here. Now there are some spots where I can draw a vertical line where I'm not touching the graph at all, and that's okay. It's just that when we do touch the graph, we can only touch it at exactly 1 point. Well, if I go right here at the y-axis, it's almost like a tangent that's happening here, where I would be just grazing the graph and touching it at 1 point. Okay, so far so good. But now if I draw it anywhere else on here, all of these lines are intersecting at 2 points. And the most we can intersect a graph with any vertical line to be a function is 1 point. So since this is intersecting at 2 points for all of these regions over here, then this is not a function because it did not pass the vertical line test. So graphs are a really great way to identify if relations are actually functions. All right, now I've got some things where we don't have a graph drawn. So if we want to test the following as being functions, well, for the first one, I've got y equals 3x minus 2. One thing I could do is I could just make a little table with an x and a y. And if I plug in a value of, let's say, 0, I would have 3 times 0 minus 2, which would give me negative 2. And again, how did I do that? I did 3 times the 0 that I'm plugging in for x minus 2. 3 times 0 becomes nothing. And then I'm just left with minus 2, and that's what my y would be equal to. So y would equal negative 2. Now I can keep doing that for other values. I could do that for 1, and I would do 3 times 1 now. 3 times 1 minus 2. 3 times 1 is 3, minus 2 gives me 1. So I would have an input of 1 and an output of 1. I could plug in 2, and I would have 3 times 2, which is 6. Minus 2, which is 4. I could plug in a 3. 3 times 3 is 9. Minus 2 gives me 7. Okay, so what was the point of listing all these? Well, now I could do a quick little sketch of this graph. So if I do 0, negative 2, have a point like that. And then 1, 1, I'd have a point like that. And then, whoops, I'd written down a 6 here before, but that should have been a 2. And I'd written down a 9 here, and that should have been 3 because I was just going through the list. Okay, so 2, I ended up having a 4. And then 3, I ended up having a 7. And again, I'm doing a very crude sketch, but we can see that this is just a line when I sketch this together. Would this pass the vertical line test? Well, does it ever cross the line at more than 1 point? 1 point, 1 point, 1 point, 1 point. It is absolutely a function. So, yes, for this first one. All right, moving on to part B. Well, part B, I have another equation, 5 equals 2x plus 6. However, how many variables does this equation have? Just one, just the x. So this is not even a relation because it's not relating two different variables as ordered pairs or as points. So this is not a relation, which means it can't be a function either. So no. Part C, I've got x equals y squared. Now I won't go through all the nitty-gritty details of this one, but if I were to try to graph this, what I would end up with is something that looks like this. It's sort of like a parabola, which we've studied. And if I flip this function around and had y equals x squared, we've done that before. And that graph, let me do a quick sketch here in blue, would look something like this, a parabola. And would a parabola pass the vertical line test? Well, sure it would. I can come down here, here, and I'm only crossing my graph at one point every single time. But if I do x equals y squared, where x is still my input and y is my output, even though I've listed them on the opposite sides of what we're used to, well, now let's pick a value for, let's say, x. And let's say x is 4. So I have 4 is equal to some value squared. Well, what squared equals 4, or what times itself equals 4? And so y could equal 2. Because 2 squared does equal 4. But is there another value times itself that equals 4? And the answer is yes. I would have a negative 2. And negative 2 times itself, or negative 2 squared, is also equal to 4. And so it's not a function because there's 2 different outputs happening here. And then as I showed moments ago, the graph would look like this sideways parabola. And we can see that because, for example, if I had that input of 4, which would be over about here, then I could go up 2 or down 2. And again, this is a pretty crude sketch here, but that's the idea. And when we do a vertical line test, I'm going to be passing through at 2 points every single time. So no, this is not a function. All right, for part D, what I've done is list a bunch of ordered pairs. And we call this essentially a set of ordered pairs because, again, it's got these little braces sort of enclosing all of our ordered pairs. We have 1, 2, so we have an input of 1, output of 2. Then we have an input of 3 and an output of 8. Seems fine. Input of 2, output of 5, input of 5, output of 14. Well, what am I looking for? I'm just looking to make sure that every time I have an input, there's exactly one output. And I have a different input every single time. I have a 1, I have a 3, I have a 2, and I have a 5. So it doesn't really matter what the outputs are. And in fact, you can even have the same output for different values. Like we would see that on a quadratic, like x squared is equal to y. I could plug in a 2. When I square that, I get out a 4. I could plug in a negative 2 and get out a 4 as well. And that's fine because as long as there's exactly one output for every input. Whereas on part C, when we had looked at that, we had an input of 4 and we had 2 different outputs. We could either have an output of 2 or an output of negative 2. So there's not exactly one output, so that one is not a function. So getting back to part D, again, for every input, there's one output. Everything seems fine here. So this is, yes, a function. Now, as I jump down to E, I've got an input of 1 with an output of 2, okay? An input of 3 with an output of 8. Again, no problem there. Now, suddenly, I have an input of 1 again. Well, we saw that at the very beginning here, and when I have an input of 1, I'm supposed to have an output of 2. But here, I'm having a different output, an output of 5, which means that I'm having more than one output for the same input, which means this is not a function. All right, so those are some different ways of looking at whether things are functions or not. And we looked at it in a bunch of different notations as well, including equations, making graphs for those equations, and then sort of sets where we list a bunch of ordered pairs there. Function notation. Function notation is a way to help organize your inputs and outputs. So likely you've seen function notation before in a previous class, f of x, g of x, h of x, anything along those lines. We even use function notation when we were doing our sequences, sort of like s sub 7 is sort of like a function notation as well. So the following are the same functions. One is without function notation here on the left, and then one is with function notation here on the right. And I find that a lot of students get really annoyed with function notation. They don't like it. And the reason I feel they often don't like it is because they don't truly understand it. So what I'm going to do is I'm going to plug in the same input here. I'm going to plug in a 2 into this function. So I'm going to have y equals 2 times 2 plus 3. So again, I replaced my x with my input of 2. And now I'm going to simplify this, and I get 4 plus 3. So y is equal to 7. All right. Now I'm going to do the same thing here. So my input is 2 again. So I have 2 times 2, my input, plus 3. But wherever I replace the x, I need to do that in every spot. So I have to have f of 2. And so now I have f of 2 is equal to 4 plus 3, and then f of 2 is equal to 7. So it kind of just seemed like I did more work because I had to keep writing f of 2. But let's say I erase all of my work in both of these cases. And so on the left, I have this answer of y equals 7. Well, when does y equal 7? What do I have to plug in to get the 7? And I don't know. There's no information given here. It just says that I have an output of 7. However, over here on the right, when I use function notation, when do I have an output of 7? Well, when I plug a 2 into my function. So f of 2 equals 7. And so what I essentially have is a little ordered pair. X was 2 and y was 7. And it's a way to help organize what you're doing. So you don't have to look back at the work. You just know that you have an input of 2 and an output of 7. And function notation is a more advanced notation because it helps organize our inputs and outputs, essentially keeping that input, that x value, and that output present at every step of our process. All right, and that is our lesson for today. We looked at functions. We looked at what makes something a function, what makes it a relation, and then used functions to find unknown values, including function notation. Till next time.